Okay, so it's time for you guys to start looking at connecting some of the electromagnetic induction stuff that you guys did to stuff that you worked on last year with light, and we're going to look at radiation and that type of stuff a little bit. So first thing we're going to do is we're just going to review some of the stuff that you guys did in grade 11, and you guys did a whole bunch of stuff with light and waves in grade 11. And let's do some review type stuff. So when you guys looked at models of light last year, we typically started with the particle or corpuscular model done by Newton, and some of this stuff should look familiar. Now this document of course is posted in your or on your class website, so either try and access it or print it off or have it handy, and then you'll have a copy of it as well. Okay, so of course we started with Newton last year. We talked about the different ways he explained different things that light can do. For example, light can reflect off of things, and he said, you know, the bullets basically bounce off stuff. Of course, light refracts when it changes angles in water and glass and that type of stuff. And of course, he said that the speed changes, but if you remember from last year, he said that things actually, light would speed up when from air to water or from air to glass, causing the change in direction. So you actually had the speed change reverse, but at least you had the change in speed part right. Okay, we talked about dispersion last year, where you had colors and rainbows when you go through a prism. And he said that colors at different speeds, and they actually refract different amounts because the change in speed is different. So some colors go straighter than others because they're faster. So red goes the straightest going through a prism, so it would be the fastest color, where blue would be the slowest, so you had different amounts. And if you remember from last year, we started with like a little ramp picture and stuff like that, and I gave a little analogy for that last year. Okay, diffraction is when waves go through openings, and of course when light goes through an opening, it basically goes straight in the shape of a rectangle, and they couldn't really explain if light was going to act like a particle. You know, you do get a little bit of slight diffraction, you know, maybe some collisions at the opening and stuff like that, but they didn't realize the whole d lambda relationship, where you want the opening to be about the same size as the wavelength for a wave to spread out like crazy. And of course, the wavelength of light is really, really small. It's kind of hard to make openings that small, but they didn't make that connection way back when. Okay, and partial reflection, you had trouble explaining that, like why when waves hit a boundary, you know, sometimes part of it will go through, part of it reflects. You couldn't really explain why the light could do that. Not a really good explanation for that, but lots of other good stuff he was able to explain. The next thing we looked at was finding the speed of light, and we looked at some of the experiments for finding the speed of light, so let's review that as well. So hopefully this will look familiar from last year. We looked at some of the major experiments in finding the speed of light last year, because they figured if light is actually traveling a bullet, they want to know if it had speed. Like, did it have an actual speed, or was it like just like an infinite speed? Like, did it happen instantaneously? And if it did have a speed, obviously it must be really, really fast. But we looked at some of the experiments last year, so let's just review some of those quickly. So one of the first ones we looked at last year was Galileo around 1600. Of course, he tried to time the lantern flashes between two mountains. Reaction time was horrible. It just didn't work. It didn't really prove much of anything, except that if it did have a speed, it was unbelievably fast. Okay, so hopefully remember that from last year. Then we looked at, in the late 1600s, Romer, the astronomer, of course, was watching the moons of Jupiter, and he noticed that the Jupiter's moon Io showed up late when the Earth was on the opposite side of the sun's orbit, and it showed that it took extra time for the light to get across our orbit. So when we were close to Jupiter, no problem, but when we were on the farther side of the orbit, it took about 16 minutes longer, because of course it takes about 8 minutes for light to get from the sun to the Earth, so about 16 minutes to do the diameter. And one of the biggest things, of course, that showed that the speed of light did actually exist. It wasn't infinite. And his rough estimation calculation, he's only about 25% off. That's really, really good. Okay. Then we started kicking into mechanical advantage type stuff last year. And remember, we have Fizeau with the spinning gear, and the light went through the sequential openings of the gear when it was actually rotating around, and used the frequency of rotation and distance and used DTV basically to get the speed of light. And then similar one we looked at last year was this one, where he used a rotating frequency of a spinning mirror in order to do the same type of thing, using frequency to get time and distance and that type of thing. And then the last major experiment we looked at last year was the Mitchelson Experiment in the 1920s, where he had the spinning mirror, and then he shot the light between the mountains, and of course the mountains increased the distance by a huge amount, and then used the frequency of the rotating mirror in order to get the timing to find out the speed of light, and he was really, really close to what we use today. So these are all experiments that we looked at last year in grade 11. in a little more detail, but this is just for review to get the ideas going again. Okay, and of course, even last year I showed you there was other experiments as well. Like in the 1930s, they started doing a similar experiment, Mitchelson again, except using a vacuum tube to make the results better. And then also last year I showed you there's a much more comprehensive list of all the experiments or major experiments that are done for like 350 years basically. And Galileo's the beginning. You can see the transition between the mechanical stuff kicking in really in the 1800s and the electrical stuff really kicking in the late 1800s and the 1900s. And of course, nowadays we use lasers and stuff like that. Okay, so this is just a general review of what you guys did last year. So back at the sheet here we have, there's those finding C, people that we're talking about. There's Galileo and got the Romer Fizeau. We got all the different experiments we looked at last year. Then after that, we started looking at the wave model of light. You guys did a bunch of stuff with the wave model of light. And one thing you guys looked at was interference patterns. And we looked how if you have two sources of waves, you could do the S1 minus S2 where you measure the two distances from a source, two sources of waves. And you see how many waves fit nicely into that difference, where the waves synchronized, not synchronized. You have maximums, minimums. And if you remember, if you had like integer number of wavelengths difference, like if one source was 5 wavelengths farther or 10 wavelengths farther or 13 wavelengths farther, an integer number, that was a nice, really good sound or high water waves, that type of stuff, that was maximum. But if they were half a wavelength off, then you got a minimum because you had crest on trough instead of crest on crest and trough on trough. So we looked at that stuff last year. You guys also did a whole bunch of stuff with Snell's law and refraction. You guys looked at that, how to find the indexes of materials and how the wavelengths change and the speeds change. And the one quantity that stayed the same was frequency no matter what. But speeds of the waves change, the wavelengths change, and this led to Snell's law. And then, of course, the big one that you guys looked at last year was the Young experiment, where we had two sources, two slits opening. The light went through there. They acted like point sources. And Young actually showed that light actually traveled as a wave, made the full interference pattern, and you had bright spots and you had dark spots, actually had light canceling itself off. Again, a good old grade 11 review here. And so you had the Young experiment, and you could calculate wavelengths by doing dy over L, where d was the distance between the slits, y was the distance between the maximums, and the L was how far it was between the slits to the actual detection screen. And then we looked at some of the geometry with the sine theta and lambda over d, and n plus a half lambda over d to get a minimum. We did that stuff last year. That is directly connected to the interference pattern stuff just above that on the sheet, because it's all the same idea. Integer wavelengths difference, maximums, lots of big waves, huge amplitude, n plus a half wavelengths, you've got minimums because things are canceling out. Okay, so these are all some of the basic ideas that you guys looked at last year. Now, one of the biggest things from last year was Hugon's principle, and how Hugon's principle works and how it was used to actually create the Young experiment and that type of thing. So let's review that as well. So hopefully this picture also looks very familiar from last year. Of course, I showed you this picture last year and the idea behind Hugon's principle. And of course, the big idea for that is that waves are always continually recreating themselves. The waves don't actually necessarily go from one place to another. They look like they do, but they're actually always recreating themselves. So every point on a wavefront is actually like an infinite number of point sources. And the constructive interference of those point sources creating the waves makes it look like the wave is actually moving forward, and when it actually doesn't. So it's kind of a tricky thing we looked at last year. We talked about it quite a bit. It's kind of an abstract thing, the whole recreation idea. So that's the biggest explanation we had last year, of course, was diffraction, and why waves, you want the opening to be about the same size as the wavelength. Now, of course, when the opening is really, really big, lots of point sources fit inside, so there's lots of interference going on. So in that middle section, you get a big flat wave going on because you get all these point sources side by side, and the waves are interfering with each other and canceling each other out, building, and you get a big flat wave in that middle section there. But when the wave opening, or the opening for the waves, becomes smaller, then you actually start limiting the number of point sources that actually will fit inside that opening. And it looks something like this. So this is what we looked at last year again. So when you make that opening smaller, now you have more of just like a single point source. All the other ones are getting blocked, so to speak. And you get nice round waves going out. So this is that nice explanation for diffraction you guys looked at last year, where you want the opening and the wavelength to be about the same size to get good diffraction. And this really explains why light typically goes straight through an opening, because of course light waves are typically so small compared to most openings that the spreading out in the sides is pretty minimal compared to the big flat part that's coming out right down the center. Okay, so again, this is what you guys looked at last year. And of course, Hugon's principle explains a few things. I mean, without Hugon's principle, the Young experiment wouldn't have worked because he had two openings like this, side by side, to act like point sources, and the waves coming from behind, they hit the openings, they recreated themselves as point sources, making round waves, and they are perfectly synchronized, perfectly identical, perfectly matched in every way to create that nice Young experiment that you guys looked at in grade 11. Okay, it also explains other things. For example, when light changes mediums and it speeds up or it slows down, but it doesn't actually accelerate because it's not the same wave before the glass and after the glass or something like that. It's not the same wave because it's been recreated within the glass and therefore takes on the properties of being created in the glass, including the speed and the wavelength of the glass. If it was the same wave before the glass and after the glass, and the speed actually changed, well, you'd have a change in V, which means you have to have an acceleration, which means you have to have a force, and none of those things apply to light. If light doesn't accelerate, light doesn't have force applied to it. It doesn't work that way. Okay, so the whole recreation idea is really important to explain, like, the refraction that you guys did in grade 11, and especially the Young experiment. Okay, so these are all just some of the basic things that you guys did in grade 11. And we're just reviewing quickly. So of course we have, the particle model and the basic Newtonian particle model, how that worked. We looked at finding the speed of light. And then of course we had interference patterns and Snell's law and finding angles of refraction. You guys even did critical angle, internal reflection, that type of stuff as well. And I showed you where the colors come from, that type of thing. And then of course the big one at the end was the Young experiment, showing that Hugon's principle definitely has a foundation. Otherwise, one wave source couldn't turn into two identical ones, and also that light then traveled as a wave to create the interference pattern. That's the only way that works. Okay, so there's just a brief skimmed over grade 11 light and wave review, and next we will start looking at applying some of these ideas, expanding on some of these ideas with some of the other things that you guys have taken.